Hello everyone, welcome back to the SEM part of our course. And today we will talk about the assumptions of covariance-based estimation and how we adjust if these assumptions are violated. The major assumptions are that the residuals are normally distributed and that the data are multivariate normal. But these are two major assumptions, and there are a few other assumptions which we also will discuss today. And the first assumption is the normality of the residuals. The covariance-based CM is a linear modeling technique, so if we assume the effect of x1 on y1, then the basic assumption is that this effect is simple and linear. But also, as this is a linear modeling technique, this means that we assume that the form of the response is normal error distribution. And of course, the violation of these assumptions require corrections, such as using transformation of data that would meet these assumptions or using generalized linear models in SEM. So now let's use an example model, which I have already specified here in Lavan. So in order to check the normality of residuals, we need the residuals themselves. And the residuals, as you remember, are the difference between each data point in our data set and the predicted values, the regression line which we are used to. And these residuals are named case-wise residuals because they are calculated for each case, for each data point. But these case-wise residuals are not calculated by the SEM analysis, and this is because of the two reasons. First, because the case-wise residuals or regression line are not used by the SEM analysis. Rather, SEM analysis uses a covariance matrix. And second is that the normality of the residuals is a prerequisite for the covariance-based CM. This means that we test this assumption even before we use the CM. And for this, we manually calculate the predicted values and then residuals. So first, for each our response variable in a model, which is y1 and y2 here, we simply fit the linear regression model using LM function. And for these models, we use function resit, and this allows us to get the case-wise residuals. And then we can inspect these residuals using the QQ plots, and the script for this you can see here. So if we inspect visually our plots here, we can see that the residuals for y1 are normally distributed. And for y2, they are not perfect, but still are okay. Another additional option is to use the multivariate Shapiro-Wilks test. For this, we can use the package MV norm test. And first we have to C-bind the case-wise residuals, which we have calculated already. And then we can use the M-Shapiro test to this calculated residuals. But also we have to use the T command here in order to transpose the rows and columns. And here you can see the output of this test, and you might be already familiar with using the Shapiro-Wilks test for the univariate normality. So this is the same principle behind the test, but instead of using one variable here, it uses multiple variables. In our case, these are case-wise residuals. And in the next slides, we will talk more about what is a multivariate normality. So we can say that our results here show that the p-value is higher than 0.05. And this means that the distribution of our residuals are not different from the normal distribution. So we can say that we can assume the normality here. Another important thing to say here is that the multivariate Shapiro-Wilks test is often too sensitive for testing of the normality of residuals. And as I have said already, the violations of these assumptions require corrections, such as using data transformation or using generalized linear models. And this can be done using package piecewise CM, which we also gonna learn during this course. And the second assumption is that our data follow multivariate normality. So let's talk now what is multivariate normal data. In the first plot here, you can see the bivariate normal data, where we have two variables, x and y, and each of them are normally distributed. But also, in addition to that, their association, their relationship, joint probability distribution is also normal. And on the second plot, we also can see the joint probability distribution of these two variables, and we can say that any linear combination of the variables is also normally distributed. This means that variable x is normally distributed at levels of variable y and vice versa. And when we have the multiple variables in our model, then we can generalize this bivariate normality to multivariate normality. We can say that variables are multivariate normal if their joint distribution is also normal. So any linear combination of the variables is normally distributed. Let's talk why do we need the multivariate normal data. This is because when we feed the SEM model, it is based on the covariance matrix. And this means that we have relationship among multiple variables here. And at the same time, the same variable can be the predictor and the response. However, if we have the increase in sample size, then the SEM models are highly robust to the violations in this assumption. The higher problem is the violation in the normality of residuals. But if we have severe violations, this also can result in a problem. We can have the inflated model test statistics, meaning that it will lead models to be rejected more often than they should be rejected. Also, we can have underestimated standard errors. This would lead tests of individual parameters to be accepted more often than they should be accepted. And now let's look again on our model example. And here I plotted the 3D scatter plot of our data for our three variables. And when we look on this scatter plot, the question is whether these data are multivariate normal. And as you might guess already, that we have some R tools that help us to test this. We can use for this the multivariate Mardias test, and we have the package named MVN that allows to do this. So when you install the package, we can use the function MVN to our data, and this package has quite different tests that can apply it here. So we specify MVN test argument equals Mardia. And here is the results from this function, and in the first part of the table we see the test for the skewness and for the kurtosis for the distribution of the data. And based on these two, the test assessed whether our data are multivariate normal. And this evidence is based on the p-values associated with the skewness and kurtosis, which should be higher than 0.05. And if p-value is lower than 0.05, as shown here for kurtosis, it means that it departures from normal distribution. And only in cases when the p-value is not significant for both for skewness and for kurtosis, then our data will be assumed to be multivariate normal. And in our case, you can see that this is not true for our example. But it's important to know here that there are no well-defined numeric cutoffs of skew or kurtosis in order to determine whether a sample distribution is sufficiently not normal to produce some problem in our SEM estimation. And that's why a test of multivariate skew and kurtosis, they tend to be sometimes overpowered. They tend to be significant even when the departure from the normality is too little to matter for the structural equation modeling. And also this test is sensitive to the sample size, with a larger sample size being more likely to produce significant results. This means that it produces non-normal results more frequently. In addition to the multivariate normality results, we get also in this table the univariate normality results for each of our variables. And sometimes we are more familiar with the Shapiro-Wilk univariate normality test, so we can request this test instead of the Anderson-Darling test here. And for this, we should use the univariate test argument here equal to SV. And you can get more information about this package by using the script here. And a nice feature of this package is that we also can get the QQ plots for our multivariate normality data. And with this, you have to use the function mvn to your data and just mention that multivariate plot equals QQ, and you will get this figure. Also, if you use the argument multivariate outlier method equal QUAN, then you will get also the suggested outliers here. Also, we can generate the univariate plots for each variable from our model. For this, in our MVN function, we should use argument univariate plot equals QQ-plot. And this will give us QQ-plots for each variable. And as you can see here, the Y1 variable has not perfect distribution on a theoretical predicted line. And if we compare this back to the results of the MVN function for the univariate normality using the Shapiro-Wilks test, we can see that it also assumes that the Y1 distribution is departed from the normal. So we can say that our data are assessed as being multivariate, not normal. And as I mentioned before, this can be just a feature of the data and our residuals are still normally distributed. And if we have very little, not significant departure from the normality of the data, we still can use the covariance-based SEM. But if we have severe violations in this assumption, then we can get the underestimated standard errors, but also not accurate estimation of the fit of the model. And there are some techniques that we can use to get the unbiased fit and error statistics. And the first approach is to use the Satora-Bentler chi-square test, and alternatively we also can use the Bullenstein bootstraps. Let's then use the Satora-Bentler chi-square estimator for our model. So this has the corrected coefficient for chi-square and for standard errors to account for non-normality of our data. In R, in Lavaan, we adjust our estimator to MLM and our standard errors to be robust, and this will allow to utilize the Satora-Bentler chi-square estimator. Also, alternatively, you can use simply argument test equal to Satora-Bentler, and this will do the same procedure for us. And here is the output of the summary function. And you can see a new thing here in addition to the chi-square statistics. So it gives the robust chi-square, which corrects for the non-normality of the data. And the correction Satora-Bentler factor is shown here. And when you want to show the values for the chi-square for the model fit, then you have to use these values, not these standard values. Also, let's have a look into the other fit measures. And for this, we have to use argument fit measures equals true in our summary function. And here is the output of this function, and you can see here that we get the robust measures of fit indices rather than the standard measures. Also, we have the robust measures of root mean square approximation and of the standardized root mean square residuals. And again, if we want to show these fit measures, we have to use these robust measures. Another option to adjust for the non-normality of data, as I have mentioned already, is a bootstrapping. For this, in our SEM function, we have to specify the argument test equal to Bullenstein method, our standard errors equal to bootstrap, and usually we use bootstrap replicates around 1000 or more. And when you call the summary function, you will see that in addition to the chi-square statistic, we get the corrected p-value, the Bullenstein bootstrap corrected p-value. And we should use then this statistic when we present the data. In addition to the two major assumptions of covariance-based SEM, we also have other assumptions which also can cause not accurate estimates of the model parameters. And one of such assumptions is that we should not have missing data when Lavan calculates the observed covariance matrix. And if we have such missing data, that might bias the parameter estimates. And for this, Lavan has the full maximum likelihood estimator, which can be applied in order to adjust for such incomplete data. For this, we should use the argument missing in our SEM function, and we should specify FIML, which stands for the full information maximum likelihood. Also, if our data are not complete but also not normal, we can use estimator equal robust maximum likelihood and missing equals full information maximum likelihood. Another important assumption is that we don't have the redundant or singular variables in our model. And these are the high correlated variables, or the variables when one variable is a linear function of another variable. But if we have such redundant variables, then our covariance matrix can be positive definite. And this would mean that we have the correlated residuals between predictors if there are linear dependency among the variables. And this is a problem because when we have two predictors, the effect of one predictor is calculated when other predictor is set to constant. And when two predictors are linear function of each other, then it is not possible to set one predictor to be constant when other is varying. So when we have such a problem, we usually get the error message from Lavan that we have the non-positive definite elements in our matrix. If we have such error, we can make the linear regression model for each of our predictor in a model, and to use the function VIF. It's a variance inflation factor, and we can apply it to our model to check whether we have the singular or redundant variables. But VIF function can be applied only to the models which have more than one predictor in order to check the singularity between the predictors. And if our VIF is larger or equal to 2, then we can say there might be some collinearity. But if it's less than 2, then we may accept that our determinants are not redundant or not singular. Another important assumption is that we need to have the sufficiently large sample size. And as you might remember from the previous lectures, that the minimum requirement is that our sample size is equal or higher than the number of path coefficients in a model multiplied per 5. In ecological data, it's not necessarily true. So if we have such violations, then we can try the local estimation procedure. For this, we can use package piecewise SEM, which we will learn on day 9 of this course. And the last assumption is that our samples should be independent. And in case if we have dependent or hierarchical data, I mean, for instance, when we have blocked design, when one plot is dependent on another plot, so we can use the linear mixed effect models or generalized linear mixed effect models together with our SEM model. And this can be done also using the package piecewise SEM. And on this slide, I just repeat what we have already learned today. So this is a protocol, what you do if you have the violated assumptions. And I will not go through these details again, as we have already discussed all of these steps. And now it's time for your task. And for this, we use again data by Grace and Kaylee, which you have used yesterday for your task. As you remember, the authors measured the cover and age of plants after the fire in California shrublands. And also they measured the fire severity. And the data are in a package piecewise SEM. But also, in addition to these three variables, they measured the richness of vegetation, the number of species, the local abiotic conditions, means the properties of soil, the spatial heterogeneity of the plots, and the distance from coast to the plots. And if you check the data carefully, you will find there are all of these variables. And now the model that you have to use in this task is presented here. So the species number or richness is affected by abiotic conditions and by heterogeneity of plots, which in turn are affected by the distance to the coasts. And also distance to the coast have direct effect to the richness. And your tasks are first to specify this model in Lavaan, and second, to check the assumptions for the covariance-based SEM. So to check the normality of residuals, the multivariate normality of the data, the multicollinearity using the function VIF for linear regression models for each response variable. And then you have to feed the model using data, Kili, and then get the fit indices. Also, to fill in the standardized coefficients and R-square coefficients for the model, and calculate indirect and total effects of the distance on plant richness. And also think, what would you say about the direct and indirect effects in this system? And when you feed this model, you will get the warning. And this is the same warning as we have had yesterday when we fitted the model for the grassland project. You can address this warning by following the same steps what we have done yesterday. And for this, you can call the model implied covariance matrix using function law inspect and check if there are no data problems, if there are no missing data, for instance. And if everything is okay, you can also check the scales of the variables, and you can use the var table function for this. And if this is a problem of data scales, then we can ignore the warning. But if you are still worried about this, you can rescale data and see if the answers changes. So this was the first task for today. Good luck with that and see you soon in the next lecture.